We are live. Welcome back, everyone. Today is our first day of going over physics. If I am rushing today, it's because A, I don't like physics and I'm not good at teaching it, but so many of you have asked for it that I'm going to try my best. I'm just going to give you the quick facts, the formulas, the things that I thought were high yield, the things that I thought you had to know. Once again, check the link in the description for everything related to this lecture series. If you're wondering why I'm dressed like this, I'm going to the mosque after this. It is the fourth day of Ramadan. So I am fasting right now, which is actually, one of you has to let me know when it's 7:02, right? That's when I have to break my fast. So I'm just going to crack open my water, and then we're going to finish up the lecture as quickly as possible. I'll go pray, and then I'll be off for the night. So one more thing, I have started a Buy Me a Coffee page. If you guys would like to donate to support the channel, that would be much appreciated. I don't make money off of these lectures or off my TikTok or anything, so if you guys would like to support the channel in that way, I would very much appreciate it. It's never an obligation, but it's always much appreciated. Also, at the end of the month, half of everything I make off that page will be donated to a charity of our choosing. So if you'd like to support charity as well, feel free. So let's get started. So let's go into chapter 1 of physics. And chapter 1 is kinematics and dynamics. So kinematics and dynamics. I'm going to have to keep my laptop quite close because I'm not at all comfortable teaching the information, but we'll figure it out. The first thing that they do, right, the first thing that they do is give you a little bit of an intro to units. Now, they talk about British imperial units and metric units. The metric units are the most important ones that you're obviously going to have to use. So let's talk about the metric system. You're using kilograms, meters, and seconds. So it's basically just kill myself, right? Kill myself units, KMS units, right? The British system, the British imperial system, does anyone know what the units are? They're pounds, feet, and once again, seconds, or foot-pound seconds, right? So these are all interchangeable between the two systems. So that's to say, when we have something like work, right, where work equals, does anyone know the formula for work? Force times distance, right? Right? And then if you're talking about work, like this is like a Newton meter, right? And then a Newton is what? It's a kilogram meter per second squared, right? So that's what that is. And then a Newton meter would be a kilogram meter squared per second squared. You can rewrite that in imperial units. So let's rewrite this. That would be like a pound foot per second squared multiplied by what? Feet. So it's pound foot squared over second squared. So it's just, you can kind of interchange between the two of them, because they are the same units, just in different phases. But you would obviously need to convert between what 1 kilogram is, 1 pound is, what blah, 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 whatever is. But they might ask you some questions on the MCAT, some discrete questions sometimes, where it's just like, what's the correct way to name this unit in the imperial system, right? Which is a really, really, really dumb way of doing that. A really dumb way of asking a question. Some special units you might need to use. So 1 angstrom looks like this. It's an A with a little halo, right? 1 angstrom is 1 times 10 to the negative 10th meters, right? It's used to measure really small things. 1 okay, we'll talk about nanometer in a second. 1 electron volt, it's a measure of energy, right? 1 electron volt is 1.6 times 10 to the negative 19th joules, right? That's 1 electron volt. We'll talk about that when we get to electricity, right? And now I just want to give you the general rundown of units you may need to know. So let's take meters, for example, right? And this is the base unit. So this is 10 to the what? 10 to the 0, right? Because that's just multiplied by 1. And what do I mean by this is 10 to the 0? If we have something that's 3 meters long, you can write that as 3 times 10 to the 0 meters. So it's 3 times 1 meters. And that's going to make sense in a second when we talk about the expansion of this, right? So let's go in the negative first. We have decimeters, centimeters, millimeters, And then we have micrometers and nanometers, right? Deci is 10 to the negative 1. Centi is 10 to the negative 2. I am going the opposite way. Hold on. cm, mm, nm. Oh. Also, that is the Greek letter mu, a micrometer, right? So let me draw it a little nicer so that you guys don't get confused. A micrometer and then a nanometer. So this is 10 to the negative 1, 10 to the negative 2, 10 to the negative 3, 10 to the negative 6, 10 to the negative 9th. So when you hear that something is 3 micrometers, I want you to think, what does micro mean? Well, first write the 3. Then what does micro mean? It means 10 to the negative 6 meters. And that's it. You just take this and drop it right next to the number that you're given, right? And this makes it very easy for conversion. So let's talk about some larger units, right? Also, there's one more that you might need, you might see every now and again. It's called a picometer. It's 10 to the negative 12th. And then we have on this side a decameter, a megameter, right? A kilometer. Actually, is mega 2 or 6? The large ones never really mattered as much as the small ones because you don't use them all that often. I'm going to leave that one empty. But this is 10 to the 1st. Kilometer is 10 to the 3rd. And I think mega is 10 to the 6th, right? So if someone says something is 5.7 kilometers, that's 5.7 times 10 to the 3rd kilometers. And now how do we convert these into numbers that we understand? Well, 5.7, and then that's a 3, right? You bounce 1, 2, 3, and you fill in with zeros. 5,700 meters, right? Same thing with our small units. If someone says to you that something is 48 centimeters, that's 48 times 10 to the what? Negative second meters. 1, 2, 0.48 meters. All good? All right. So that's units. And those are going to be exceedingly important the more and more we go into physics. Let's talk about vectors and scalars, right? So what's a vector? Magnitude and direction. It is a symbolic way of showing any sort of force or thing with magnitude and direction, right? And a scalar is a magnitude with no direction, right? So let's talk about vectors because scalars aren't really that important. So here is a vector, A, and here is a vector, B, and this is one of the first things you ever do in a physics class. You add the two vectors together, right? So you add the horizontal component here and the vertical component here, and you get a resultant vector, C. And you say A plus B equals C. Right? And that's important because when you have a vector like this, let's call this vector X, actually. You can split the vector into components. You can split the vector into a horizontal and a vertical component. Who likes trigonometry? I love trigonometry. I think it's awesome. I love trig, right? So here is an angle theta. And if you guys remember SOHCAHTOA, right? So sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. and then tan is opposite over adjacent, so SOHCAHTOA, right? We can calculate vectors A and B using what? SOHCAHTOA, right? So if we know the angle measurement, then that means that sine theta equals what? Opposite over hypotenuse, which is going to be B over X. And if you know theta and you know X, you can solve for B. It's just going to be X sine theta, right? And that makes sense because sine theta is going to be less than 1, right? And then X, when you multiply that out, it's going to reduce X down to its vertical component, right? What's next? How are you going to get A? Cosine, right? Cosine theta equals vector A over X. So that means that B is X sine theta, and A is X cosine theta. And this holds true whenever you draw this diagram. This holds true absolutely whenever you draw this diagram. When you draw it like this, that's how it's run, right? So when you have, like, let's say you're doing kinematics, and you have something on a slope like this, right? And it experiences a normal force this way. When you split up the normal force into horizontal and vertical components going down, you're going to do the same thing. You're going to do the exact same thing. Oh, sorry. Normal force this way. And when you split this normal force into horizontal vertical components like that, you're going to do the exact same thing you do over here. And we'll talk about that in a second. Also, if you don't have theta and you have A and B, what are you going to do? Well, tan theta equals B over A, and that means that theta equals inverse tangent B over A. Gotta remember that trig. You don't need to know like the law of cosines or anything like that, but that much trig you have to remember. Okay. What is displacement? It is a vector quantity of distance, right? It is a vector quantity of distance. So let's say I started here, and I move 3 meters. If I just say 3 meters, that's a scalar. If I say I moved 3 meters to the east, that is now a vector, and that is a displacement. My total displacement was 3 meters in the what? The positive direction. Let's set our positives, right? This is our positive, and this is our positive. If I move 3 meters in the positive direction horizontally, that is a displacement, right? So distance vector connects an object's initial position with its final position with a straight line. So let's say our object started here, and our object ended up here. This is our distance vector, our displacement, right? And our displacement can be broken up as our horizontal displacement and our vertical displacement, right? And we're going to use the same laws that we used over there in order to do so. How you doing, man? What's going on? Nice to meet you. What's your name? Yusuf. Nice to meet you, man. Take a seat. So, knowing displacement, what is velocity? Well, has anyone here taken calculus before? I've taken calculus. Have you taken calculus? Calculus? Yeah? All right, so calculus? Never taken calculus? All right, I'm going to blow your mind right now. So there's this thing called calculus called a derivative, right? And a derivative is a function over time. And basically, you take the slope of a certain line, and you just look at that given slope at a specific point, right? So the velocity, if you're calculus-minded, is the what? It's the derivative of distance. And then the derivative of velocity would be acceleration, right? So the distance moved over a period of time is going to be the velocity. So if we were to write it in physics terms, the velocity is actually the limit as the change in time approaches 0 of delta x over delta t. right? And delta x being the displacement, right? But this just means that your average velocity is this, right? The change in distance, the change in displacement over the change in time, correct? So average velocity differs from average speed, right? Because what? The difference between displacement and distance traveled, right? So if I drive my car from here to Montreal, right? My displacement, right? So let's say this is New York City, and up here is Montreal. My displacement is going to be this, right? So if it took me 6 hours to get there, my total displacement is going to, my total velocity, my average velocity is going to be this delta x, this change in position, divided by the number of hours it took to get there. But my average speed is going to be what? I didn't drive in a straight line. I hope I didn't, or else I ripped through a bunch of buildings and probably killed a couple people, right? My average speed is going to be my distance along this entire path from New York to Montreal divided by the amount of time. That's my average speed. So speed and velocity are two completely different things. One of them is a vector quantity. One of them is not, right? Or one of them is dependent upon a vector quantity, right? What is, in the most basic terms, what is a force? What is a force? A force equals mass times acceleration, right? But other than that, a force is a vector quantity experienced as pushing or pulling against an object, right? So let's say that we have a block. So force is a vector quantity of pushing, pulling against an object. If my handwriting is worse than usual, I've probably taken 40 pages of notes in the past week, so I'm very, very exhausted of writing. My USMLE is in a week. So, what do we measure forces in? We measure them in newtons. And remember, the way that I always want you guys to think about physics is whenever you hear a unit that's not basic, break it down into basic units, right? So we just said that F equals MA as a little bit of foreshadowing, right? So that means that we can rewrite these as their basic units, where newtons equals kilograms times, what's the unit for accelerations? Meters per second squared. Meters per second per second. And how do we get that? Well, we know that the derivative of displacement is velocity, and the derivative of velocity is acceleration. So if we have displacement in meters, and the derivative of that is velocity, then the derivative of that is acceleration, meters per second divided by seconds. So meters per second times 1 over second equals meters per second squared. Right? So that's how we derive the unit of acceleration. So a 1 Newton, and I want you to remember this forever, 1 Newton is a kilogram meter per second squared. That is one of the most basic things that you must remember about physics. A Newton is a kilogram meter per second squared. Because then you can elaborate on that whenever you're working with newtons, where work, like we said earlier, is force times distance. Now that we know that a Newton, this guy, is a kilogram meter per second squared, we know that work in its basic units is a kilogram meter squared per second squared. Also known as what's the unit for work? A joule. So that's a joule, right? And we can verify that. How? Well, we know what else uses joules. We know energy uses joules, right? So energy, like let's say kinetic energy, equals 1/2 mv squared, right? Well, velocity squared is going to be meters squared per second squared. Multiplied by velocities, multiplied by kilograms is going to be kilogram meters squared per second squared. Do these match up? Yes, they do. So physics can be cross-referential, right? You can cross-reference between different formulas and units and make sure that you're doing things properly. So let's say that you forgot how to derive the thing for work, but you know that work is exactly like energy. Just use the units from energy. Figure it out. Right? All right. What is gravity? It's the attractive force felt by all forms of matter, and we have a formula for it. The force of gravity equals big G m1 m2 over r squared. The mass of the first object, the mass of the second object, divided by the distance between them, squared. And what is this big G? It's the gravitational constant. It's the gravitational constant in the universe, right? And big G is equal to, they'll probably give it to you, but unless they're bastards and they don't, it's equal to 6.67 times 10 to the negative 11th. I'm not going to give you the units. I want you to tell me what they are. Use this and tell me what the units are. It's your first assignment in physics. Let's look. So we're solving for the units for G, right? The easiest thing to do in physics is always to get the thing by itself first, right? So G actually equals FR squared over M1, M2, which means the units for G would be the units for all of these put together. So it's going to be a Newton multiplied by meters squared over kilograms squared. And that's actually how they write the units for G. Newton meter squared per kilogram squared. But if you wanted to be fancy and take it a little step further, you know that Newton's is what? What did I say Newton's was? Kilogram meters squared per second squared. So that's going to be a kilogram meters squared per second squared multiplied by meters squared per kilogram squared. That goes away. This guy becomes meters to the fourth over seconds squared times kilograms. And those don't really make any sense to us, but that's why it's a constant, right? What's an equation without a constant? It's called a proportion, right? So all we're saying here is that the force is proportional to the masses divided by how far away they are. And then once you add in the constant, it becomes an equation. Like what's the constant here? What's the constant? Speed of light. We're saying that energy and mass are proportional. The moment we drop the constant in there, it becomes an equation. Okay. What's friction? What's friction? It's a force that resists what? Motion. It's a force that resists motion. There's two types of friction. Who can tell me the two types of friction? Static and kinetic. Static and kinetic, right? So what's static friction? The best way that I describe this is the way that my physics teacher taught it to me. He took a shoe, right? He took a shoe and he put it on a slope, right? And the shoe didn't move, right? And then he took the slope and he unwound it from here and lifted it slowly until what? The shoe slipped. Until the shoe slipped and then it kept falling, right? What was he displaying to us right there? So here's the normal force on the shoe, right here, right? And then here's the what? The horizontal and vertical component of the normal force. And why is the horizontal component and vertical component going this way and this way? Oops, sorry. I keep drawing this wrong. I haven't done physics in so long. Here's the normal force on the shoe, right? And here's the horizontal and vertical component of the normal force, right? And why does it go this way? It's because we set the positive as that, right? So, that being said, when he lifts this, all he's doing is increasing the force of friction on the shoe. He's increasing the force at which it's being pulled down. So, as it sits here, there's a force going this way, and that is the force of static friction, FFS. Right? And FFS is equal to mu S Fn. Right? Mu S Fn. Right? But it has to be less than that. Because once you cross over mu S Fn, you're going to start sliding. And once you start sliding, there's no coming back. Right? So static friction exists when a stationary object exists between a stationary object when it rests on another object. Right? So what we're saying here is that the force of static friction is 0 less than force of static friction less than mu S Fn. And this is going to be a constant, and this is dependent on the weight of the object. Also, what's weight? Mg, right? Mg is weight. And m little g, right? Weight or force is mg. What's little g? For the MCAT, what's little g? 10. 10. It's 9.81, but on the MCAT it's 10. Right? So the force of static friction needs to be between here in order for it to be viable, in order for it to be actually doing anything. Right? Even if it's 0.0000001, it's still doing something, but it can't be a single tenth of a percent over this, or else it's going to start sliding. And when it starts sliding, what do we call that? We call that kinetic friction, right? And kinetic friction is just Fk equals mu Kfn. And the last thing, the MCAT's never really going to ask you about stuff like this. They're never going to ask you about kinetic and static friction, things like that. How you doing, boss? I got your email, by the way. Thank you so much. I'm sorry I didn't get to reply to you. The one thing they might ask you about is a conceptual thing, where they want you to know that mu s is what? What's the relationship between mu s and mu k? Mu k is smaller than mu s, because before you move, you have to stick. Before you move, you have to stick, right? All right. Good? It's all right? Everyone kind of understands how to go about thinking about that? You might not need to do a question like this, like for the friction and all that stuff. I can't remember the last time I ever saw one of those. A lot of the physics on the MCAT is just more conceptual than it is anything else. Which is why, honestly, like, let me tell you guys something. I never wanted to teach the physics. I am doing this completely against my will. But the moment I started uploading videos on the YouTube channel, and thank you guys so much for watching, by the way, I really appreciate it. The moment I started uploading to the YouTube channel, are you doing physics? Where are the physics videos? Do you teach physics? Do you do this? Do you do that? I was like, I don't, but I will. I will try. So you guys can give me feedback and tell me how I'm doing at the end and all that stuff. Also, huh? Right. Also, at the end of the month, at the end of this month, at the end of March, I'm going to send out like a little like satisfaction survey. Serafina and Ben, who are the two people at Brooklyn College who were kind enough to let me teach here, they just want to know how I'm doing. So, and they want to like gather some information for following year, some recommendations, some stuff that we can do to make the program better for next year. So I would really appreciate if you guys take part in that. So what is the difference between mass and weight? What's the difference between mass and weight? Well, mass is just the literal what? The matter in my body. The matter in my body. Every atom, every cell, every single bacteria that I hold inside of me, the matter inside my body. What's weight? It's the way that the matter interacts with gravity, right? So this is just mass, all of the stuff that's inside me, measured in kilograms in the metric system. And then this is weight. And it's the force due to gravity. That is my weight. So I weigh 168, 170 pounds, right? And that is the mass inside my body as it interacts with gravity, right? One more thing. Gravity is what? It's a type of acceleration, right? Because this is a force. And we know, because classical physics, we know that F equals ma, right? So G must be a form of A, right? And G is just the A that the Earth exerts on everything on it, right? So this is an acceleration, isn't it? And that means that it is a change in velocity over change in time. Or a change in displacement over a change in time over a change in time, right? So if there were no other factors, which there never will be, but the physics we do will always assume there are no other factors. If I were to jump out of a plane, right? From the first moment where I have zero velocity, 1 second later, how fast would I be going? I'd be going 9.81 meters per second. The next second, how fast would I be going? An additional 9.81 meters per second, right? In the next second, how fast would an additional 9.81 meters per second? That's what the acceleration due to gravity means, right? Also, one more thing. I am a human being. This is me. This little black dot, that's me. And I'm standing on the surface of the Earth. Imagine if I was that huge in respective to the size of the Earth, right? It is pulling me in with Fg equals mg. And what I'm pushing down, it's pulling me in, and it is pushing me back. It is pushing me back with, what is this thing called? The normal force. Fn equals mg. Because they cancel out. I'm not moving, right? And that's another thing that we have to talk about. When things are static, when things are not moving, the sum of the forces upon that object is 0. So if-then statements are really important. If object is stationary, then sum of the forces on the object is 0, right? So that brings us up to a really, really good point of discussion, Newton's laws, right? The most basic laws of physics, the ones that you always learn the moment you enter a class. Our great physics daddy, Newton. Number 1, the net force on an object is its mass times its acceleration. Sigma F equals ma. Who knows the second? That's the first. So, not a body in motion stays in motion. An object at rest. An object at rest will stay at rest. Is that it? Unless acted upon by not just a force, an unbalanced force. Because if that word unbalanced wasn't there, right? Let's say that I was an object, I'm a cube, right? And there's a force pushing me this way, right? Of 5 newtons. But there was also a force pushing me this way of 5 newtons. Am I moving? No, because that would violate the first law. The sum of my forces is 0. So the sum of my forces is 0, and that means that my mass times my acceleration is 0. And my mass isn't 0 because I exist, so my acceleration must be 0. You know what's funny? I watched this video about how all the laws of physics work with negative masses. Isn't that interesting? Even like the upper level like theories of like relativity and quantum stuff, they work with negative masses. It's weird. Try to wrap your head around that one. But then again, it was like a 45, 60-second video of a dude just like showing how you can like plug in negative masses and stuff like that. I'd want to look into it more, but like it's like weird. I used to be a huge physics nerd, like back when I grew to hate it. back before I grew to hate it. I love like theoretical physics. I just don't like applying it. I actually thought about being a physicist at some point. Okay. And then the third one, everyone knows this one. For every action, there is an equal and opposite reaction. Good? Still don't know how to write on a whiteboard. It's been months. How long have I been here? I've been here since like August, right? September? It's been a while. I like counted the number of hours of lecture I have up on my channel now. It's like 50. I think I have like 50 hours of lecture up on there. It's crazy. Hello. How you doing? Oh man, I gotta kind of breeze through this. All right, linear motion. Let's do the equation. So motion with constant acceleration. V final equals V naught t plus AT. Oh, sorry. No, V naught plus AT. My bad. How you doing, boss? Long time no see. So V final, and this makes absolute sense, right? And look why this makes sense. Why does this make sense? Because when you take the acceleration, you multiply by time, what do you get? You're undoing the derivative. You're undoing the derivative, right? You get velocity. So you're saying velocity final plus acceleration times time. And why does this make sense? Remember when I was falling out of the plane? I was falling out of the plane. You guys just walked in. Yes, I was falling out of a plane before. So remember I was falling out of the plane, my initial velocity was what? 0. And for every second that I fell, I increased my velocity by 9.81 meters. Why? Because I did it per second squared, and I multiplied by the number of seconds, that's going to give me my final velocity. So if I fall out of a plane for 10 seconds, and my initial velocity was 9.81 meters, my initial acceleration was 9.81 meters per second squared, and it stayed that way, because I don't have any air resistance, right? I'm just going to multiply by 10 seconds, 98.1 meters per second. I'd be falling from the sky at 98.1 meters per second, right? Okay, next. Vf squared equals V naught squared plus 2a delta x, change in displacement, right? Same thing, same idea, right? Why? Because Vf squared is going to be meters squared per second squared, and this is going to be meters squared per second squared, and this is going to be 2 times meters per second squared times meters. And then that's just going to be meters squared per second squared. Easy, right? Easy enough. Why is the 2 there? Bro, I don't fucking know. I'm not a physicist. I should not curse, I'm fasting. All right. They love this one. They absolutely adore this one. X final, your final position is equal to your initial position plus your velocity, your initial velocity times the amount of time you were at that initial velocity, plus 1/2 times your acceleration times t squared. Why does this make sense? This is meters. This is meters. This is meters per second times seconds, which is meters. This is 1/2 of your meters per second squared times seconds squared, which is meters. Remember, if you guys ever mess up the equation, break it back down into the units, right? And the last thing, your displacement, your final position, is your average speed multiplied by your time. Good? Now, when are you going to use all of these? It really depends on what you've been given, right? It really depends on what you've been given. If you're just given a initial velocity and you know the acceleration and then you know the distance traveled, you can use this one, right? If you want to find the end position, you know where you started, you know the initial velocity, you know the acceleration, you know the amount of time, you can use this one, right? Does that make sense? So you have to have a little bit of information for all of them. You can't do this one without the final position. You can't do this one without all of this, but you can do it without the final position because you're solving for that. It just depends on what you're solving for. So don't think of when can I use this equation on the fly. Think about how can these equations get me to where I want to be? What do I want? If I want the final velocity, I'm either using this or this, depending on how much information I have. If I want the final position, I'm using this or that. Right? Okay. Inclined planes. Very important. This is the thing I was talking about before, breaking stuff up into sines and cosines. I'll ask the question again because some people just entered. Does anyone like trigonometry? I love trigonometry. I love trig. Trig is awesome. That was like one of the last times that I genuinely felt like joy doing math. Trig and Calc 1. All right. This is an inclined plane. And this is an object on an inclined plane. Say it's an apple, right? The normal force from the plane is perpendicular to the position of the apple, right? So this is the normal force that's exerted on the apple. This is Fn. It's like this. I kept messing it up earlier. I kept wondering whether it was this way or this way, but it is this way. I'm looking at my notes right now, right? Someone quote me on that though. Hold on. Let me see. Is it perpendicular to the plane or to the surface? But this is perpendicular to the surface, right? Okay. So perpendicular to the surface. I haven't done physics in so long. Just want to make sure. Because now I'm like tripping myself up. Yeah, so it's going to be perpendicular to the surface, and then you have everything else. Okay, so why did I lock my computer? Then you're going to have a vertical and blah, blah, blah component of the force. This is theta. What theta is that? That theta is that theta. How? I forget. I forget how to prove that. And then this is the force of friction going not that way, not that way, going this way. Right? And this is mg cosine theta, and this is mg sine theta. Why do we have this split up like this? Well, because Fn might be going that way, but which way is gravity going? Straight down. This is mg right here. So the reason we have that isn't to break up the normal force, it's to break up the force of gravity. Because if we clear that one more time, right? We look right here, this is the normal force, but this is the force to gravity. This is Fg equals mg. So we need to break this up into mg cosine theta and mg sine theta. So in this diagram, if this thing wasn't moving, what is Fn equal to? Mg cosine theta, because that's the vertical component of the gravity that is pulling down on, and now it's all coming back. Now it's coming back. The vertical component of the gravity is opposite the normal force. And if it's not moving, that means those two have to be equal, right? And if this also isn't moving, that means we're using static friction, correct? And that means that the force of friction is equal to mg sine theta. Very good. Mg sine theta. Why? Because there's one more thing that I didn't tell you guys to do. Whenever you draw a diagram like this, set your positives. And I used to draw them like this. These are my two positives. Positive this way and positive that way. Don't set them in the plane of gravity, because you're going to break gravity into the positives anyways. We just broke gravity into our positive plane. Does that make sense? Yeah? You guys be able to replicate that if I gave you a question about it? You want to go over it again? Okay. It's a mosquito or some sort of small bug. So these are inclined planes, right? So once again, just to recap, the normal force is perpendicular to the plane it's perpendicular to the plane, right? FG is straight down. And it can be split up into mg cosine theta, which is always going to be opposite the normal force in a diagram like this, and mg sine theta, which is going to be the component opposite friction. Because it's going to go this way and this way. That make sense? Yes? So the normal force is perpendicular to the plane, right? And then FG is straight down. So if we were to rewrite this whole diagram with simplified forces, we could write it like this. Fn mg cosine theta mg sine theta, and what's going this way? Ff. Now, what's going to happen is that the sum of the forces is going to be equal to the mass times the acceleration, right? The mass of the apple times the acceleration. So if you had the apple rolling down the hill, that means that what? And we set positives like this, right? This is how you approach questions like this. If the apple is rolling down the hill and they tell you that it's rolling at a certain acceleration, they made your life a hell of a lot easier. That means that the mass times the acceleration is equal to mg sine theta minus force of friction. And since it's rolling, we know that is that. Yeah? Does that make sense? So this is how you kind of set up to solve problems like this. Why do I not need to give you numbers? Because once you have numbers, it's easy. Once you have numbers, you're good. You're chilling, right? Because let's say you were solving for the acceleration, right? All right, get the acceleration by itself. Mg sine theta minus mu k. Fn is what? Fn is just like we said, mg cosine theta divided by m. A equals this. M gone. A equals g sine theta minus mu k g cosine theta. Right? And that means A equals G times sine theta minus mu k cosine theta. And that's a very classic equation for a question like this. I'm sure you guys have seen these before if you've taken physics, right? Someone call me out if I made a mistake. I make mistakes every now and again. I don't think I did, right? So MA equals mg sine theta minus mu k fn. Mu k fn equals fn equals mg cosine theta. Mu k mg cosine theta, cross off the m's because you're dividing by m. Take out the g, you get sine theta minus mu k cosine theta. It's one of the first problems you'll ever do in kinematics. So never put in the numbers until you have the entire equation set up symbolically. Okay. It's also one more thing for circular motion. We have something called a centripetal force, which is equal to mv squared over r. mv squared over r. And that's it. It's chapter 1. It's almost time for me to eat. I'm excited. But before I eat, let's talk a little bit about chapter 2. This is what? Work and energy. There's only a couple things that I want to talk about because all of this is conceptual. All of it is just stuff you're going to read straight out of the book. So this chapter is straight formulas. Kinetic energy equals 1/2 mv squared. Gravitational potential energy. So this is kinetic. What is gravitational potential energy? mgh. So if I'm standing at a cliff, if I'm standing right at the edge of a cliff, right here, and the cliff is 50 meters tall, and I am, how many kilograms is like 160 pounds? Like 70? 70, something like that? Let's say I'm 70 kilograms, right? What's my potential energy? 50 times 70 times 10. So what, 35,000 joules? All right, 3. Who knows what this one's called? Who knows what it's called? Elastic potential energy. Why is this important? This is why it's important. You have a wall, you have a spring attached to here, and it's stretched out a certain, so this is where the spring normally is when it's not stretched. You stretch it out a certain degree, and you attach a little ball to it. You let go, you want to know how quickly is the ball going to accelerate back towards the, what? The wall, right? And you can find the energy of this entire thing by the spring constant, which is a constant to all springs, and multiplied by the distance that you stretched it squared, right? And what does this have to do with acceleration? Well, you can substitute these for any of these. All of these are equal to one another because all of them are measured in joules. Joules. What is a joule again? Remember, guys, all the way back. So why is this called work and energy? Because work and energy use the same units. So what is work? Work is force times distance. And we said that a force in newtons was what? Kilogram meter per second squared. And a distance is meters. And that means that work is kilogram meter squared per second squared. Well, if work is kilogram meter squared per second squared, and that's a joule, that means all of these guys are kilogram meter squared per second squared as well. Kilogram meters per second squared times meters. Kilogram meter squared per second squared. Meter squared per second squared multiplied by kilograms is kilograms meter squared per second squared. This guy is meters squared, which means this guy is kilograms per second squared. So you can derive it as well. The total mechanical energy of an object, which is known as E, is its potential energy plus its kinetic energy. So if I'm falling out of the goddamn sky, right, and I'm 50,000 meters in the air, really high up there, right, and I'm falling with a specific velocity, you can calculate my potential energy and my kinetic energy, add them together, and you'll get my total energy. right, which is known as total mechanical energy. Now, why is that important? The conservation of energy, right? The moment I start falling faster out of the sky, I lose a little bit of distance and displacement from the Earth, correct? That loss in height translates to a gain in kinetic energy, right? And the moment that I go splat on the floor and die, all of the energy gets transferred into a force against the Earth, right? So that conservation of energy is always going to happen. Now, and when I go splat, if you touch the ground by where I went splat, it'd probably be quite hot because that kinetic energy turned into thermal energy, right? That's a big thing that they ask you about in physics way, way, way later. When we have E equals hc over lambda, they're going to say that a photon with a specific wavelength was emitted with X amount of energy, right? But they say, right, that X amount of energy, it is 7:02. It means it's time to eat. Okay. After one sip of water. So E equals hc over lambda. They're going to tell you that the photon was emitted with a specific amount of energy. But, right? You can calculate the energy of the photon. Then they're going to say, hey, if in reality E plus whatever amount of energy was absorbed by the photon, right? How much, well, they're not going to tell you that. What they're going to say, they're going to give you a wavelength of a photon, right? And then they're going to say, we actually put this much energy into the sample, right? How much excess energy was absorbed by the detector, right? So basically what's happening is, let's say that you have an atom and you have a little electron here and you're waiting for it to emit a photon of light. You irradiate this thing with energy and it emits a photon of light at a specific energy, but the energy that you put in, this E1, was greater than E2. Well, you know, because of the conservation of energy, that the energy couldn't have gone to waste, right? So all the energy that the photon didn't absorb and emit back out in the form of the photon is going to get detected by the detector. So you need to use the wavelength, multiply the Planck's constant by the speed of light, divide by the wavelength, find the energy, subtract it from your E1, and then tell me what the energy on the detector was. And it's a very simple question. Because you know what they're going to do? They're going to give you the wavelength. So if they give you the wavelength and they give you the E1, all you have to do is E1 minus hc over lambda. That's it. That's it. That's the excess energy that was detected by the detector. That's a very common question on the MCAT. And it seems so complicated, but it's very simple. Work. For some reason, guys, and someone help me figure this out, because clearly you're much better at physics than I am. They say cosine theta in the book. What gives? What is cosine theta? Why do they say FD cosine theta? Well, I actually forgot. So you guys figure it out for me. And come back next time and we'll talk about it. What else can we do with work? We can find something called, what's the derivative of work? You said it. Power. Power. Measured in watts. Watts. I'm going to erase that because I don't want you to think I'm multiplying by anything, right? So that means that FD over T equals power, which means MAD over T equals power, which means MVD over T squared is power. How do I do that? V divided by T is A, right? So T squared. Or MXD over T cubed is power, right? And I'm just breaking these down to their most simple sort of units just to show you that if a force is a kilogram meter squared kilogram meter per second squared times meters divided by seconds. We're going to get kilogram meters squared per seconds cubed. And that is a watt. That is a watt. They talk a little bit about, the last thing they talk about is efficiency and mechanical advantage. Mechanical advantage comes up on the MCAT every now and again because it's something that people always forget. It is the force out divided by the force in. So basically, if you have a system, like a pulley, and you pull with 5 newtons, but you're able to move a massive force, the mechanical advantage of the pulley is how much force it outputs given your input, right? You want something with the highest mechanical advantage possible at all times, right? This is why we use things like what? Wrenches. So let's say you have a wrench and you push down right here. Your force that you're putting right here is getting multiplied by what? The moment arm. And that's something we know as torque. Torque gives you mechanical advantage, right? You can put out more torque given a smaller thing if you're further away from the object, right? That's why you push doors from the furthest from the hinge. It's easier to push a door further away from the hinge than closer, right? We'll talk about that when we talk about torque. But mechanical advantage, they might ask you one question about it. A mechanical advantage is the force output by the system divided by the force input. And a good mechanical advantage is greater than 1. That's mechanical advantage, but it's the same thing as efficiency, basically. And honestly, the rest of it is conceptual. There is a short section in the chapter about like force, pressure, volume diagrams, all that stuff. The same thing that kind of goes on in like chapter 8 of chemistry. There's a reason I didn't teach that. I don't know it too well. And other than that, that's it. That's all I have to offer you for the first 2 chapters of physics. I know it wasn't a lot, but I hope it was enough to get you guys started on your route to getting a perfect score in the section like I did. So I don't know how the hell that happened, by the way. But thank you guys so much for coming. Thank you for watching. Thank you for sticking around. Once again, you can find all the links to everything associated with this program in the description. And donate to charity and donate to the Buy Me a Coffee if you like my lectures. Thank you guys so much for attending. And I have some bad news. The program will be over in another 5 weeks. So we have 5 more weeks of time together. We will finish in the final week of April. We will finish in the final week of April.
During the spring break?
When is your spring break?
19th of April. 19th of April to
We will end in 4 weeks. We'll end before spring break. Yeah? Or we could have 1 session or 2 sessions after spring break. We'll figure it out. But anywhere between 4 and 6 weeks. So plan accordingly. If you guys were looking to take the MCAT, right? Plan accordingly for the end of April or sometime in May. Joseph, I believe you said you're taking it in May, correct? Or sorry, end of April. Yeah. I know some people want to take it in May. So plan accordingly. We should be done with physics quick because there's some chapters I'm just not going to teach. There's some chapters I'm not going to touch. Optics? No. Absolutely not. No optics and no fluid dynamics. There is no way in hell I'm ever looking back at any of that, right? As important as it is to ophthalmology, I don't want to do ophthalmology, right? All right, so thank you guys so much for watching, and I hope you had a good time. If it was your first time here, thank you for coming. I'll be here munching on my sandwich because I'm really hungry, so come up and ask me a couple questions, and I will see you guys next time.